Jonathan. Quick replacement change here to the schedule because unfortunately one speaker couldn't make it. So as you see, I have presented this earlier in April already as part of a PSI webinar. But since that was a different region, different audience, I thought it's kind of worth repeating it here. And it's about a fun kind of project and language, which is Julia. So let's have a look. So we'll quickly introduce Julia, then talk about two projects. The first one is about Bayesian joint survival models. The second one is about Bayesian safety signal detection. So you see some common theme there. And then I talk about why R loves Julia or why Romeo loves Julia. So how do they fit together very, very nicely. I will skip the openstatsware part because this is a slightly shorter slot here today, and I talked about that already yesterday. Okay, so what is Julia? This is the kind of logo that we have from the programming language. And how do I relate to Julia personally? So I'm personally very excited about Julia because our initial two projects, and when I say our, I mean here the Roche kind of context, but that was also the personal initial two projects. These were pretty successful. Yeah, I'm not actively learning right now, but I have definitely started learning the basics of Julia only, so I'm by far not an expert. And the other interesting fact is that Julia is my first new programming language since a bit of C++ before started learning that before 2010s, using that still when needed, and a bit of Python when I was at Google. I bought a book, Algorithms with Julia, that I can recommend, but I haven't really finished reading it, to be honest. It sits on my shelf, waiting for me to come. And we have basically run a Julia course at Roche in Basel with a couple of folks there in basically the whole first half of this year. And that was also fun to learn a lot new things about Julia, and doing that collectively was really good. So what is Julia? Julia is a high-level general-purpose dynamic programming language, most commonly used for numerical analysis and computational science. That's the Wikipedia summary. Importantly, Julia can be run interactively, just like R and Python. That makes programming feel very familiar and relatively easy. It's a pretty new programming language. So the development started only in 2009, so that's 15 years ago at MIT. And the 1.0 release and stable syntax only came out in 2018, so 6 years ago. If you compare it with Python, where the first version was released in 1991, and R, where the development started in 1991, you see there's almost a 20 years difference. So it's really like the next generation after R and Python. Julia is an open source project, and there is a Julia Hub company which also receives funding. What is Julia not? Maybe a contrast here. I would say it's definitely not a drop-in replacement for R or Python, at least for the stuff we are talking about here at this point. I would also say it's likely not a mainstream language in the next 10 years or so. It's not a large language model, okay, because we heard a lot about LLMs and generative AI in the 3 keynotes in particular. But you can actually build, train, and deploy LLMs with Julia if you like. Maybe that's not the most common thing to do, but you could do it, and I put a link in here. Why is Julia called Julia? So there's something which is related, which is the Julia set, which is a mathematical concept. And this code, which I adapted here from Mehdi Hanet, is actually now using Julia code. And besides producing this very nice image here, which is an image of a Julia set, you see a little bit about the syntax here. So we have some using statements, similar like in Python. We have no brackets here for function definitions, indentation only. That's also like in Python. We have some kind of vectorization here going on. For example, you see this dot star here. This is the broadcast operator. So here we say we want a kind of element-wise multiplication, and So it is quite nice, quite easy to read. And the other interesting thing is sometimes you don't have any classes defined. So for example, here for these parameters, whereas here you have a class or type definition, right? You say here you want a complex float, 64 bit. Um, so that's also pretty powerful. I think I will mention a little bit about it in a second as well. So how does Julia look like in practice, or what is my practical experience so far? So we tried this in two projects, and here they come. So the first one was about Bayesian joint survival models. And there was a project with Yannick Amann from ETH Zurich, and there were also Doug Kerkhoff and François Mercier from Roche Genentech heavily involved. And this is about implementing specific joint models for time to event and longitudinal data. So you can have a look at the book by Rizopoulos for more background. And an important application here that we looked at in particular was how can we correlate, model together the survival of patients and the tumor size over time. So basically, that's the longitudinal data that we were looking at. How can we do that, right? And the good news is that here we could successfully implement these models based on Turing.jl, which is a probabilistic programming framework, similar like, for example, Stan that you might have heard about if you are doing Bayesian inference. And we also published this open source as jointsurvivalmodels.jl. So if you search for that, you find that. Otherwise, later I'll show you the link to the slides and then you can just click on it. Very quickly, not very much in detail, how does the model structure of a joint model? Again, you have a longitudinal process. Here, let's just say you have a single outcomes. So that could be a typical nonlinear mixed effects model, for example. Then here you have a baseline hazard describing, let's say, the underlying survival of your patients. Then we have a link coefficient. So that's just a real parameter gamma here. And then we have this link operator on the longitudinal process. So basically that defines what's the kind of summary that we take from a longitudinal process to impact the hazard. And typical examples are to take, for example, the derivative of our longitudinal process. So think about tumor size, right? It's probably a bad sign if the tumor suddenly kind of explodes. So you have a higher rate there. Derivative will be larger. Or you can look at the integral, right, of this longitudinal process. And then you can think about many other things. And then you can basically say, well, the hazard for my joint survival model, the hazard for the patient survival is basically in a similar way, like in the Cox proportion hazards model, is just a multiplication of the baseline hazard and this impact term here. So we have this x perm, x transformation to make it positive. And then inside we have this link coefficient times the link operator, basically, right? And you see here already the challenge. This hazard can be potentially quite complicated. So that's why we have some computational challenges. Because for the likelihood calculation, of course, we need a survival function. And in general, there's no closed form for the survival function, right? So that's why we need to numerically integrate the hazard function to obtain, first of all, the cumulative hazard. And we can do that very nicely here with the integrals.jl package, Julia package. And of course, we also want to maintain full flexibility for defining the model functions. So in particular, that means what's the link operator? Maybe we have some other covariates we want to put in this exp term, right? So for that, we use Julia functions to stay flexible. And then how do we estimate the parameters? Again, mentioned before, we use Turing.jl to run Markov-Chain Monte Carlo to produce here our Bayesian inference results. So a very small glimpse here how this looks like. This is not even the complete, let's say, end-to-end example, of course. But for example, here I just show you some code. We load here our package using joint survival models. We define a longitudinal process. This is like some nonlinear thing here involving cosine and and power terms and so on. Then we have a baseline hazard, right? I think this is viable when I remember correctly. Then we have a constructor here where we call here this joint survival model thing. So we basically define, we have a joint survival model. This is our baseline hazard. This is our link coefficient here coming here from this final function definition. This is basically a function joint model. And then here we have a longitudinal process, right? Now we call our function, our custom constructor function, to create an object. Okay, so we say, A is 1, B is 2, gamma is 0.3, alpha is 0.5, theta is 0.8. So we make it very concrete. So we really have now defined a function. And then the cool thing now is we have methods defined underneath in this joint survival models package, such that when we want to call this complementary CDF, which is the survival function, over a range of time points, then it just works, right? So it looks like magic, but underneath we have everything going on here, numerical integration and so on and so on. Right? And then we can just plot it, for example. So that's then what you need to really make the inference. So I didn't show here anything about Turing and so on, but you can find all of those details on the repository, of course. Okay. Jonathan, just let me know when I'm running over, right? I think I still have like 7 minutes or so, or 6 minutes, right?
Yes.
Okay, cool. Second project, Bayesian safety signal detection. And again, this is also Bayesian. So we'll also use Turing. It started with an idea coming from Susan Robson. There was also a methods group involved, so Kasper Rufibach, and then Giuseppe Palermo implemented the analysis in the end. And what was the idea? What was the work to do? They basically found a nice paper by Christian Brock and colleagues, and they wanted to implement it. They wanted to use it, right? Unfortunately, the authors couldn't share the R stand code. So what was the alternative? I thought, well, instead of just doing the whole thing again in R and Stan, why don't give you Julia a try, right? So I quickly chatted with Christian. He already had some Julia code snippet for the very, very first part. So I started from there. And actually, after having like something working after 1 day, which is super fast for this kind of complex model, in my experience, we said, okay, let's just build the package. So we built the safety signal detection.jl package, and it's also open source available now. Okay, so how does it work? I will go pretty quickly over this. And if some of these keywords are interesting to you, then you can look more in detail. But the first step is to get samples from a meta-analytic prior. Okay, because the idea is we want to derive a prior, this meta-analytic prior, for the adverse event probability in the control arm of an ongoing blinded trial, right? And why do we do all of this? Because the idea is we have a blinded trial ongoing, and FDA and other authorities require us to kind of monitor that for safety signals. So even though it's blinded, we still need to have an idea. We need to have some kind of red flags going on or some red lamps going on when some adverse event rates for some kind of type of adverse events are too high, right? And this is kind of a formal way to do this, right? So let's say we have some historical trials. For each patient in these historical trials, we had some outcome, let's say for this specific adverse event type, right? I'm just looking at one type of events. Of course, we have some time at risk as well. So for these patients. And then we assume some certain beta distribution on this kind of trial specific event probabilities, okay? And we say the blinded control arm should basically follow the same distribution. So they should be kind of exchangeable, right? And the cool thing is now it's relatively easy, and I will not go into details, but then with Turing.jl, it's relatively easy to create posterior samples from this blinded K+1, so the additional new kind of control arm. And those are then our meta-analytic prior samples for the actual analysis. But before doing that, we actually want to, let's say, approximate this a little bit. So we just get some samples from this MCMC, but now we want to have a closed form for this prior. So how do we do that? And why do we do that, right? It makes sense to only do the step one once, because we need to run the safety analysis potentially like every day or every week or something in the trial, right? So we don't want to run out of this machinery again and again. Of course, we could, but we can approximate also this samples by a closed form. And in many cases, like mixtures of distributions are very powerful to do that. And here, because we are between 0 and 1, right, we have a probability parameter. Here we can mix like beta distributions, and often 2 of them are already sufficient, right? And these are defined, these mixtures of distributions are already defined in a distributions.jl package, and we can use expectation maximization algorithm enabled by another package to fit the parameters of these. Okay. And the last step is then to do the blinded trial analysis, so the actual application, right? So we assume basically for each patient, because they are blinded, we don't know which arm this patient came from, control or experimental arm. So we just say, as an approximation, we say, well, we know the randomization ratio, maybe 2 to 1. And if it's 2 to 1, then we assume, okay, with probability 66%, this patient came from the experimental arm, with probability 34% or whatever, we assume came from control arm. So we have a mixture kind of likelihood for this patient. And then when we define this and so on, we crank our MCMC machinery, and we obtain then posterior samples for these AA probabilities. Okay. And then we can do all kinds of summaries. So for example, look at the posterior probability that the adverse event rate in the experimental arm is higher than in the control arm, right? And we can ring some bells if this probability is too high. So what were the computational challenges here? The EM algorithm uses internally a weighted maximum likelihood estimation method, but the corresponding method was not yet defined. It was just not yet there for the beta distribution in distributions.jl. So first what I did, I wrote down with pencil and paper the Newton-Raphson algorithm for the weighted maximum likelihood for beta, and then implemented the corresponding Julia code and declared the method in my code, in my script. And the great thing is it just works together with everything that was already there from the packages, okay? That's because of the powerful method definition way in Julia. There was some other details which I will skip over now. And then you get something nice like this in the end, but I will skip over this now. So why is it working together very well? And I know that I'm already running out of time. Julia is easy if you know R, okay? You can try out in this terminal, which is called REPL. It has a familiar syntax. You don't need typing, but you can use typing. As I mentioned, you can naturally extend this via new types and this multiple dispatch. If you know S4 and R, it's very similar, but actually much easier in Julia. There's some overview of the differences available as well. And what we used here in these projects, Julia can be called easily from R. So with this Julia connector package, it's very easy to use. We have used this. You can just start with your data input handling and data wrangling in dplyr and R. Then you apply your Julia code with the custom local module, and then you go back to R. So you will really then only need to use Julia for what you need Julia, right? Okay. This I will skip over. You can also use it from Quarto, no problem. Some things even feel easier, so you can have a look at this later. I will skip over all of this, okay, and just come to the end. If you are looking into all the details, look at danielinteractive.github.io r-and-julia. Okay, cool. That's it. Any questions?
Thank you very much. So the one question from the chat is Julia easier than Python?
Yeah, I'm not a Python expert. I found it easier to start learning if I compare my own experience. But of course, it's not a mainstream language and it's not a general purpose language. So if you want to learn something for, get more bang for the buck kind of thing, then probably you want to learn Python. But if you're really interested into very, very efficient numerical computations, implementing algorithms, and so on, then Julia can be definitely worth it.